Hi, George Diamond here. We're continuing our video series on derivatives. I brought my bucket with me. Let me put my bucket down. This is my blue bucket. Now, we've already looked at an introduction to derivatives, and we're going to move on now. We're going to start looking at some of our basic rules for derivatives. So we're in this particular section here. Now, in our textbook, this is section 2.2. Okay, this is basic differentiation rules and rates of change. In this section, this is very, very important. What we're looking at in this particular section, we're going to be looking at the general power rule for derivatives. The big one. We'll be using this rule literally for the rest of the year. So it's very important that what we're looking at in today's video lesson, that we understand this really well, because we're going to be using it in the other rules. There's actually four major rules for derivatives. You've got the basic power rule, you've got the quotient rule, product rule, and the chain rule. So there's four of them. And this is the key, though. If we can do this rule right here pretty good, this will give us a really good start in being able to work derivatives. Now, to start off, though, we've got a couple of essential questions. Now, our first essential question, what are the four basic differentiation rules? All right. Now, we're going to look at just four. We'll look at these four here. What are the derivatives of sine and cosine functions? We're going to be looking at that, how to get the derivatives of sine and cosine. Okay, also, what do derivatives have to do with rates of change? So we'll be looking at velocity, some velocity problems here. Now, on the PowerPoint here, I basically want to follow you through my PowerPoint. On the PowerPoint, I've left off the examples and things. Now, on the next video, we're going to do a bunch of examples of how to find the derivatives using our shortcut rule, if you will. Now, we're already familiar with the longhand derivative rule. So the limit as h approaches 0, etc. So we did that in the previous video. So we're somewhat familiar with the longhand method for calculating a derivative. Now, what we'll be doing in this lesson is we're going to find a shortcut. So derivatives that would take us several minutes to find the derivative of. Okay, now we're going to take seconds to find the same derivative. So a very, very important lesson today. This is the type of lesson we'll be using for the rest of the year. So very important. So let's get started. Okay, with what's called the constant rule. It says the derivative of any constant is 0. Okay, that's it. Okay, that's called the constant rule. The derivative of any constant is 0. So let's start off with an example. This is a general expression. So the derivative of c with respect to x, so the derivative of any constant is 0. Now, if you think about a constant function, let me bring an example up here. Now, there's a couple of examples on the PowerPoint here that we're going to look at. These are some really simple stuff. Some of the more, a little bit harder examples we're going to save for the next video. Right? But there's a couple of them here that I'm just going to kind of, hopefully just get these down and kind of follow me through a couple of real simple examples. Okay, let's start off with the y equals 7. Now, when you think about it, if you think of the graph of y equals 7, y equals 7 is a horizontal line. Right? The slope of a horizontal line is 0. Remember, the derivative is slope. So the derivative of y equals 7, we say y prime is 0. Because remember now, the derivative gives us a slope, right? So if your line is a horizontal line, okay, then we're talking about a slope of 0. Right? Next, what about f of x equals 0? Well, once again, another horizontal line. The derivative, you got it, 0. What about s of t equals -3? Well, -3 is a constant. The derivative of any constant is 0. There you go. So s prime of t, so the little dash here indicates prime. So s prime of t, that's a notation for the derivative, is equal to 0. Okay, what about something like this? Y equals k pi squared. So I use pi for squared, or for pi. So k pi squared, where k is a constant. Now, if k is a constant, not a variable, right? You've got a constant here. The derivative, you're right, 0. So y prime equals 0. So if you look at the graphs of any of these, the graphs are all horizontal line. The slope of any horizontal line is 0, so the derivatives are all 0. That's the first rule. Okay, second, now this is the big one. Okay, this is called the power rule for derivatives. Now, like I said, this rule here, we'll be using for the rest of the year. Basically, the rest of the year. Very important that we look at this rule here. And this is how it starts off. It says if n is a rational number, then the function f of x equals x to the n is differentiable, and this is true. So to get the derivative of x to the n, So this is x, where n is an exponent. You bring n down as your coefficient, and then you subtract 1 from your exponent. So two things happen in the general power rule. Okay, the exponent comes down in front of the function as a product. So instead of x to the n, it's n times x. So the exponent becomes a factor, and then you minus 1 from your exponent, and that gives you this is a shorthand rule for the derivative. And without this rule here, we would have to use the long way with the h. The limit as h approaches 0. We would have to use that longhand formula. This keeps us from having to use the longhand formula. So derivatives that we used to have to take several minutes to calculate the derivative of, now we're going to take the same derivative within seconds. It's going very, very quickly. Okay, we're going to be able to get the derivative of stuff using the power rule here. So once again, just to review, the exponent becomes a factor. All right? So instead of x to the n, it'll be n times x, and then you subtract 1 from your exponent to get the new exponent on the derivative. So let's run through a couple of simple examples. There's some more examples on the next video that we're going to run through. We're going to do a bunch of examples on the next video. Okay, let's look at a couple. Find the derivative of each. So a couple examples. Here's our first. Okay, f of x equals x to the third power. Now remember what we said, we're going to bring the exponent down front and then subtract 1 from the exponent. So you do the derivative. F prime of x is going to be equal to, now instead of x to the third power, this is now 3 times x to the 3 minus 1 power. So you subtract 1 from your exponent, and the derivative becomes 3x to the third power. So where 3 was your exponent, it's now being multiplied to the x. Right? So it becomes like a coefficient, if you will, times x to the second power. Now notice, the original function here was x to the third, a cubic. The derivative is a parabola, x to the second power. Right? So it's going to be one degree less than the degree of the original function. And keep in mind now, the derivative itself is a function. It has its own graph, its own x-intercepts, etc., just like the original function. But once again, you take the exponent, bring it down, and multiply to x, it becomes a factor, and then subtract 1 from your exponent. That's your derivative. Much faster. Like I said, we can do this. We're going to do this in seconds rather than minutes, like we used to do with the longhand formula. Let's do another one. X to the 2/3 power. Now, once again, you bring the 2/3 down as an x, and it becomes a factor, so it'll be 2/3 times x. So instead of x to the 2/3 power, it's 2/3 times x to the 2/3 minus 1. Now, just remember now, when you subtract 1 from 2/3, this is 2/3 minus 3 over 3, which would be negative 1/3. So when you subtract 1 from 2/3, you're going to get negative 1/3 for your new exponent. And the derivative becomes, well, you can just barely see it here. Okay, the derivative becomes 2/3 x to the negative 1/3 power. Okay. Now we'll do another example here, a real simple example. This is 1 over x to the second power, a fraction. Now later on, you're going to see something called the quotient rule, which we can use on complex fractions. But now, a simple fraction like this, if we can, we want to use the power rule on it because it's a lot faster. All right, so 1 over x squared, let's rewrite this using a negative exponent. I'm sure y'all remember now from your algebra classes that 1 over x to the second power is the same thing as x to the negative 2 power. All right, so we're going to rewrite that. 1 over x squared equal to x to the negative 2 power. Now, once we've written it in exponential form, all right, now let's use our general power rule on it. The negative 2 comes down front as a factor, and then minus 1 from your exponent. So that's like this here. The derivative g prime x is equal to negative 2 times x to the negative 2 minus 1 power. So to describe the derivative, this is negative 2x to the negative 3 power. So negative 2x to the negative 3 power. Now, let's move on. Let me see if we have another example. Yeah, let's try another example here. Okay, let's try a slope example. It says, find the slope of f of x equals x to the 4th power at each of these x values. Now, we looked at in the previous video, we looked at getting slope. You find your derivative and then substitute in for x, and that'll give us the slope at any particular x value. Right now, Got our function here, x to f of x equals x to the fourth. To start off with, though, let's get our derivative. And like I said, we're not going to use the longhand formula, let's use the shortcut. Now, to get the derivative of x to the fourth, you bring the 4 down front, and then subtract 1 from your exponent. So the derivative becomes 4x to the third power. Very quickly, we got our derivative now, right? So instead of x to the fourth, the 4 now is being multiplied to x to the third, or to the x, and then you minus 1 from your exponent gives you x to the third power. So this is our derivative. So now, to get our slope at x equal -1, all we have to do is substitute in for -1 and for x. Let's do the first one here. So this represents our slope. This is now a slope expression. And we can find the slope on the curve of our original function at any particular point. Now, all we have to do is substitute in for x, and it'll give us a slope on that graph. So let's do the -1 first. At x equal -1, take the -1, plug it into your derivative for x, and we get 4 times -1 to the third power. Well, -1 to the third power is -1 times 4 gives us -4. So at x equal -1, the slope should be -4. Now, let's do x equals 0. All right, now, once again, here's the derivative is a slope expression. So substituting 0 into the derivative now gives us 4 times 0 to the third power. Now, 0 to the third power, 0 times 4 is 0. So at x equals 0, the slope on our curve here is going to be 0. Let's do one more. Let's do the +1. So at x equal 1. Now, once again, we're going to substitute 1 in for x. That gives us 4 times 1 to the third power. So substitute the 1 into your slope expression, into your derivative. Now, 1 to the third power is 1 times 4 gives you +4. So, very simple matter now to get the slope. If you can quickly get your derivative, plug your x value in, substitute it in, bang, there's your slope. All right, so very quickly we can get the slope. If we know the x value, all we do is substitute it in. Okay, let's move on. Okay, let's look at something called the constant multiple rule now. So the constant multiple rule. Now, this is what the constant multiple rule says. Now, a little note that the derivative of x is equal to 1. So the derivative of x is equal to 1. Now, let me show you why this is true. Now, you remember the general power rule for derivatives. It says you take x is the same thing as x to the first power. Now, according to the general power rule, when you take the derivative of x to the third power, okay, this would be 1 times x to the 1 minus 1 power. Okay? Now, 1 minus 1 will give us the new exponent, which is 1 times x to the 0 power. And remember, anything to the 0 power is 1. So you end up with 1 times 1, which is 1. So that's why the derivative of x, just a variable, is 1. So basically it's a coefficient. So the derivative of 1x is 1. And that's why. That's because of the general power rule. It's the same thing as x to the first power, which is 1 times x to the 1 minus 1 exponent. And you end up with x to the 0 power, which is 1. Now, this is called the constant multiple rule. Now, if you have a constant times your function, you take the derivative, use the general power rule, times your constant multiple. So if your function already has a coefficient, you multiply the coefficient times the exponent. So let's look at an example here real quick. We've got a couple of simple examples on our PowerPoint we're going to look at, and some others in the next video. We'll look at some a little bit harder examples. Now let's do this here. Here's our original function, f of x equals 3x to the third power. Now, according to the constant multiple rule, 3 is our constant multiple, times x to the third power. All right? Now, to find the derivative, we would take the derivative, f prime x is equal to, you bring the 3 down, 3 becomes a factor now. So you already have the 3 there to start with. Now you got 3 times x to the 3 minus 1 power. So 3 times 3 times x to the 3 minus 1 to get the new exponent. Now you got to remember to subtract 1 from your power, from your exponent to get the new exponent on your derivative. And then you multiply the coefficient and the exponent, or the old exponent and the coefficient together. And the derivative is 9x to the third power. All right, so as you would bring the exponent down front as a factor, if it already has a coefficient, you would multiply the exponent and the coefficient together. So 3 times 3 gives you 9. Subtract 1 from the exponent gives you x to the second power. The derivative is 9x squared. Okay, let's try another one. What about 1/4 x to the second power? Well, to find our derivative, you're going to bring the 2 times 1/4. Right, so take your exponent, becomes a factor now, a multiple, so it'll be 1/4 times 2 times x to the 2 minus 1 power. So subtract 1 from your exponent. Now, 1/4 times 2 is 1/2, so it'll be 1/2 times x to the first power, or just 1/2 x. Now, these are just simple examples. I can just kind of show you these on the PowerPoint. And like I said, in the next video, we'll do something a little bit more complex. Now, let's do another example. What about y equals 2/x? Now, to begin with, let's rewrite this. 2/x is the same thing as 2 times 1/x. Now, remember the example we looked at earlier? 1/x, this is a fraction. These simple fractions, we need to rewrite those with a negative exponent. So, 1/x is the same thing as x to the negative 1. Now, a lot of times when you're finding the derivative of a function, the hardest part of getting the derivative is rewriting the function. So sometimes you got to rewrite it because the general power rule uses the exponents. So, if you have radicals, you want to rewrite them in exponential form. Little fractions like this, you want to rewrite them with negative exponents if you can. Now, more complex fractions, you have to use what's called the quotient rule for derivatives. Now, to take the derivative of 2x to the negative 1 power, it'd be negative 1 times a positive 2. So negative 1 times positive 2, then subtract 1 from your exponent. Now, the exponent is already negative, right? So negative 1 minus 1 is going to give you negative 2 for the new exponent. So the derivative becomes negative 2x to the negative 2 power. All right? So once again, negative 1 times 2, you take your exponent times your coefficient, minus 1 from your exponent, there's your derivative. That's the general power rule. And let's see if we have, now remember, negative 2x to the negative 2 power is the same thing as negative 2/x to the positive 2. Because remember, typically you don't want to leave your answer with a negative exponent, so you can go ahead and rewrite that as negative 2/x squared. Now let's do this example here. Here's another pretty simple one. Okay, we have negative 3x over positive 2. Now that's the same, you can pull that x off. That's the same thing as negative 3/2 times x. Now here we have a coefficient of x. When you take the derivative here of just an x expression, basically what you end up doing, the derivative here is going to be negative 3/2. So when you take the derivative of just an x expression, basically what you do, you end up dropping the derivative. And you're dropping the x variable, or dropping the variable, and the derivative is going to be your coefficient. So the derivative here is going to be negative 3/2 x. And you just basically drop the x. Okay, let's move on to what's called the sum and difference rules. Now, this applies to polynomials and stuff like this, where you have maybe several different terms being added or subtracted together. And this is what the sum difference rule says. If you're taking the derivative of a sum, right, so f of x and g of x are two separate functions, you're taking the derivative of f of x plus g of x. Well, what you have to do, you have to use the power rule 2 times. Take the derivative of f of x and the derivative of g of x. So you take the derivative of each one of your terms, and then you end up adding them or subtracting them, whichever the case may be. So the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. So you just take the derivative of each term and leave it added or subtracted, and then simplify it if you have to. Now, same thing is true for subtraction. You're taking the derivative of f of x minus g of x now. Right? So this time you're subtracting the two terms. Well, when you take the derivative, you take the derivative of f of x minus the derivative of g of x. Same thing. Just take the derivative of each term, and in this case, you leave them subtracted. Right. Now, look at an example. We're going to do a simple example here just to kind of illustrate what we're showing. Let's try a cubic polynomial. Okay, f of x equals x cubed minus 4x plus 5. Now, to get the derivative, now you have to take the derivative of all 3 terms. Okay? Now, start off. The derivative of x to the 3rd power is 3x squared. Now the derivative of minus 4x, remember, if you only have an x variable, you're going to drop the x variable and leave the coefficient. So the derivative of negative 4x is just negative 4. And remember, the very first rule we looked at was if you have a constant, the derivative of 5 is 0. So you just drop the 5. Right? So the 5 we just drop. And in our derivative then, as you look at our function here, you got x cubed minus 4x plus 5. The derivative of x cubed is 3x squared. minus the derivative of the middle term, which is minus 4, and then the 5 on the end, you just drop. All right, the derivative of 5 is 0. That would be an example of the sum difference formula or rule. Okay, another example, let's try this one right here. So another little polynomial type function. Now, as you find your derivative now, you take the derivative of the first term. Okay, you're going to multiply 4 times negative 1/2 and then subtract 1 from your exponent to get the new exponent in your derivative. So what this, as you take the derivative of each term, this will be negative 1/2 times 4 times x to the 4 minus 1 power. That's going to give you the derivative of the first term. Now, as you take the derivative of 3x to the 3rd power, this will be 3 times 3 times x to the 3 minus 1 power. And the derivative of 4x, you know what I said, if you have just an x expression, you drop the x. So the derivative of minus 4x is just minus 4. And then as you simplify, negative 1/2 times 4 is negative 2x to the 3rd, plus 3 times 3 gives you 9, and then 3 minus 1 from the exponent gives you the new exponent, which is 2 minus 4. So the derivative of g of x would be negative 2x to the 3rd plus 9x squared minus 4. So just a little, any type of polynomial function like this, you take the derivative of each term and then add or subtract as appropriate. All right? And this is our second example. We'll look at it some more, like I said, in the next video. Now let's take a look at the derivative of sine and cosine. Now let's do sine first. So the derivative of sine and cosine. Now consider the graph of the sine function. Yeah, so this is the graph. So remember, it starts here at 0, 0, goes up to pi, over to 2 pi here. So this is the derivative of the sine, or the graph of the sine function. I'm sorry. So this is the graph of the sine function. Now, what I want to do is this. I want to graph several points on what will eventually be the derivative of the sine function. So I'm going to start me a little chart over here on the side. So we're going to make a graph of the slope. All right. So we're going to find several points on what would be the derivative of the sine function. So we'll make a little graph of the slope. So over here to the side, I'm going to start me a little chart with the theta versus the slope. All right. So the theta versus the slope. So let's start off with over here. Let's let theta be negative pi. So over here is negative pi. Now, what I'm looking for here now is we come up with a graph of what will be the derivative of the sine function. If you look at the graph right here, okay, the slope at negative pi, if you can imagine, drawing a tangent line to the curve at this particular point, at negative pi. First of all, it's going to be a negative slope, right? And it would be just like this here. As a matter of fact, the slope here would be equal to negative 1, right? So if you look at that point on the derivative now, it's going to be the point negative pi, negative 1. So let's go ahead and put the negative 1 right here, okay, for my first ordered pair. Now, negative pi, negative 1 is going to be a point on the derivative of the sine function. Okay, and you can see that right here. Let me erase this. And you can see that point right here. It's real small. But that point right there is going to be a point on the derivative of sine. Okay, next, let's try the next point. Okay, let's try negative pi over 2. Now, negative pi over 2 would be here. Now, if you look at the area shaded in yellow here on our graph, if you were to draw a tangent line to the curve right here, okay, this will have a slope of 0. So at negative pi over 2, let's put in our next slope. It's matching slope there, which would be 0. Now, if you look at that point now, this is another point on the derivative. So negative pi over 2, 0 is going to be right here. So let me get my green marker. It's going to be right there. It's going to be another point on the graph of our derivative. Now, let's try next. Let's try right here at 0. Right. Now, notice, if you were to draw, here's 0, 0. If you were to draw a tangent line to the curve, it'd be like so. Now, the slope here would be equal to positive 1 again. So the slope here would be equal to positive 1. And now that would be at 0, so as we look at our next ordered pair would be the ordered pair 0, 1. Right? Now, the next point we want to try, the next x value, or theta, I guess, would be pi over 2. So pi over 2 is going to be here. So we're talking about the slope of our tangent line right there. Now, once again, this has a the slope of 0. So as you look at our next ordered pair on our derivative, it'll be pi over 2, 0. So we're going to put the 0 in here for pi over 2. Now, let's locate that point. Now, one point was 0, 1. Let's locate that one up here. So this point here is pi over 2, 0, which is right here. That's another point on the graph of the derivative. And we got one more point we want to try. Let's try this one over here. You can see it shaded in yellow. Now, this is at pi. Now, if you draw a tangent line to the curve, so if you draw a tangent line to the curve, okay, this one's going to have a slope equal to -1. So let's go put -1 in at pi. All right, so that's -1, pi -1. Now, pi -1 is going to be down here. So -1 directly across to right there. Now, you can see the green dots. Now, the points in green, those are all points on what will be the graph of the derivative of sine x. Now, what we're going to do next is connect all the dots. So we kind of erase some of these right here, so you can maybe see it a little bit better. Erase this, let's erase this right here. Now, let's connect all the dots so you can see what the graph of the derivative will look like. So here goes. See the one in red? Okay, as you look at this graph, everyone should recognize that the graph in red, okay, that's the derivative of sine, and the graph in red is the cosine function. You can see it starts up here, down, and back up. So as you look at this graph, that's the cosine function. So the resulting curve is a cosine curve. So we say, never forget, this is the derivative of sine x is cosine x. The derivative of sine x is cosine x. And once again, this is something that we'll be using for the rest of the year as we go through calculus, right? You got to remember the derivative of sine is cosine. Now, we're going to do the same thing. Let's come on over to the graph of cosine. All right, so we can do the same thing for y equals cosine theta. All right, so same thing. Now, let's see what the graph of the derivative of cosine will look like now. Now, remember the derivative of sine was cosine. So let's see now, would the derivative of cosine be sine? Well, let's check, that's what we're going to see. So let's start off with, right here at negative pi again. Now if you look at the derivative, the slope of your tangent line here at negative pi would have a 0 slope. So the slope here is 0. So our first ordered pair on the derivative would be negative pi 0. All right, now that'll be right here. Now next we're going to try at negative pi over 2. So let's come over here just like we did on the other one. I'm going to do this pretty quickly. So you look at the slope of your tangent line, that'll be a slope of 1. So at negative pi over 2, we say the slope, that'll be the point negative pi over 2 at 1. Okay, next let's try up here at 0. Now you draw your tangent line, you can see this has a 0 slope too. So you have a slope of 0. If you draw that tangent line to the curve at 0, so the next ordered pair here will be 0, 0. Now once again, remember that's another point on the derivative of cosine. Now let's come on over. Okay, let's try pi over 2 right here. Now if you draw this tangent line to the curve, that's it. Now this has a slope equal to -1. You can see how it's decreasing from left to right. Right, so at pi over 2, that ordered pair is going to be pi over 2, -1. And then one more place, and let's try pi. Now if you draw your tangent line to the curve, you can see you have it's going to be a horizontal line, and the slope is going to be 0 again. So at pi, the resulting slope will be 0. So pi 0. Now let me see if I can erase this, and let's take a look at our points now. Now what we want to check let's see if, okay, let's see, now we said the derivative of sine was cosine, so let's see if the derivative of cosine is sine. Now, let's take a look at our points. Let me make these a little bit bigger so you can see them here to 1 point. Okay, negative pi over 2, 1 is up here. 0, 0 is here, that's the origin. And then pi over 2, -1 is down here. And then the last point is right there. So you can see we got 5 points plotted. Now, let's take a look at this graph right here now. Dang, that is not the cosine function. As a matter of fact, this is the cosine function that's been reflected over the x-axis. So the resulting curve is a sine curve that has been reflected over the x-axis. So this is actually it's not the sine, it's the sine function reflected over the x-axis. So if you look at the derivative of cosine, the derivative of cosine is not sine, it's negative sine x. The derivative of sine is cosine, but the derivative of cosine is negative sign. Now this is just one way to kind of illustrate how you get these, how we get the derivative of sine and cosine. So let's bring this up on the next slide. Nice and big, so everybody can see it. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. So 2, now there's going to be 6 trig functions by the time we get finished, but now this is 2, you need to commit these to memory. So when you're looking at a function that contains sine, you need to recognize now its derivative is going to be cosine. Right? The derivative of cosine is negative sine. So 2 things we have to commit to memory. So whenever you see that, automatically you need to recognize what the derivative of sine and cosine is. So I think we have an example or 2. So let's find the derivative of each. Let's do 2 sine x. And we said the derivative of sine is cosine. So the derivative of 2 sine x will be 2 cosine x. There you go. If you know what the derivative of sine is, easy to do. Let's try another one. And we're doing a couple of simple examples here. We'll do a little bit harder ones on the next video. Now, cosine x over 2, that's equivalent to 1/2 cosine x. Right? Now, we said the derivative of cosine is negative sine. So the derivative of 1/2 cosine x would be negative 1/2 sine x. So that's your derivative. So y prime is going to equal negative 1/2 times sine x. All right, so easy to do. And I said we'll do some more examples in the next video. Now just remember, to have a derivative, a function has to be continuous and smooth. Now we went over these in a previous video, but I want to kind of touch on them again just to make sure we remember where the derivative doesn't exist. Now you already have this in one of your notes, I'm sure, but the derivative fails to exist if you have a sharp corner, like f of x equals the square root of x. So you got a sharp corner, no derivative. If you have a cusp, like you see here, right? So this is y equals x to the 2/3 power, so a cusp. At the cusp, no derivative. Also, if you have a vertical tangent line, so anywhere you have a vertical tangent line, like right here, your derivative is slope. The slope of a vertical tangent line is undefined, so there's no derivative here at 0, 0. And anywhere you have a discontinuity, so vertical asymptotes, no derivative. If you got a jump, no derivative. All right, let's move on. Now, most of the functions we study in calculus will have a derivative, so most of them are going to have a derivative. Now, let's take a look at something called the intermediate value theorem. Now, this is called the intermediate value theorem for derivatives. It says if a and b are any 2 points on an interval on which f is differentiable, so once again the function does have a derivative everywhere, the derivative takes on every value between f prime a and f prime b. All right, now I'll show you kind of what that means here with a little diagram, right? But keep in mind, if a and b are any 2 points in an interval on which f is differentiable, so once again the function has to have a derivative everywhere on the function, then the derivative takes on every value between the derivative of a and the derivative of b. So take a look at our graph here. And here's my curve. All right, now let's bring in, let's let a be here and b, now a is, let's say at a, let's say the derivative of a is 1/2. Now 1/2 is fairly flat, all right, so not very steep at all. So the derivative here is 1/2. Now let's put point B over on the other side here. So point B is over here. Now you look at the slope of point B, very steep. So the derivative at B is 3, let's say. All right, now, according to the intermediate value theorem, there has to be some place between A and B where the derivative is 1. There has to be some place where the derivative is 0.75, 1.5, etc. So the derivative is going to take on every value. So there has to be some place in here where if you were to draw the tangent line, okay, the derivative would be equal to 1. So that is the slope of your tangent line would have to be equal to 1. 1 is between 3 and 1/2. So, you know, all those values, it's going to take on every value between 1/2 and 3. So there's going to be a tangent line in here for every value between 1/2 and 3. This is called the intermediate value theorem. All right. Now, let's move on. So between A and B, f prime must take on every value between 1/2 and 3. Now, let's take a look at rates of change. Now, in our next video, we'll look at some examples here, but just some descriptions as we get started. The derivative is used to describe the motion of an object moving along a straight line. So we use derivatives to describe motion along a straight line, velocity and acceleration, etc. Now, let's describe the position function of a function, all right? So given for motion along the line. So the position function is, this is the function that gives the position or positions of an object relative to time, right? So this is a position function. So simply the function that gives the position of an object relative to time. And like I said, we'll look at some examples on the next video, but right now this is just some vocabulary and stuff that we want to kind of introduce everyone to. All right, so rates of change. So rates of change is velocity. So now first of all, let's let delta t be a period of time. All right, so this will be a period of time. Okay, let's let delta s be a change in position. All right, so a change in position. Now also you remember that your rate is equal to the distance divided by time. So rate is the velocity, right? It's also the first derivative is distance divided by time. Now the average velocity, now we describe average velocity. Average velocity is the change in distance divided by the change in time. Right? So the change in distance divided by the change in time, right? Which is described as delta A over delta T. Now I'll tell you what I want to do real quick. Let me go back on that and let me use the same expression that we used in pre-cal, in their pre-calculus class. Now in pre-calculus they use S of T2 minus S of T1 divided by T2 minus T1. So in pre-calculus they use this to describe average velocity. Now average velocity is simply slope of your secant line. Right? So when you look at average velocity, it's simply what would be the slope of a secant line between 2 points on a curve, on a time distance curve. Right, let's move on. Now, using the derivative, right, now the derivative gives us instantaneous velocity. Now, average velocity is 2 time intervals, if you will. Now, instantaneous velocity says if s equals s of t, so you have a position function, right? Okay, this is the position function for an object moving along a straight line, right? Okay, the velocity, or the instantaneous velocity, is the limit as, and now we use h instead of delta t. I use the terminology in your textbook, but the limit as h approaches 0 of s of t plus delta t minus s of t over delta t. Okay, this is basically, if you remember, this is the longhand version of the derivative. So instantaneous velocity, to get instantaneous velocity, we use the derivative. So the velocity function is simply the derivative of the position function. All right, so here's the key. This is the derivative of the position function. Right? So this is the derivative. Now, we know how to do shorthand derivatives now, right? But when you talk about instantaneous velocity, this is simply the derivative of the position function that will give us the instantaneous velocity. Now, average velocity, you have to use the slope, we just looked at on the previous slide. But now, to get instantaneous velocity, we use the derivative. Now, a little note about velocity. Velocity can be negative, positive, or 0. So it can be either one, right? But now speed, now remember, speed is the absolute value of velocity. So speed cannot be negative, right? So speed cannot never be negative, right? Now, if you remember I guess the formula for a free-falling object is described like so. And I'm using this is out of your textbook, right? So your position function s of t is 1/2 times g times t squared plus v sub 0 times t plus s of 0. Now, any of you that have had physics, I'm sure you've probably seen this expression or this function for a free-falling object, where s of 0 is the initial height of the object. So s of 0. So if you throw an object, if you're, for instance, if you're 50 feet up in a tree and you throw an object, throw something, a rock out of the tree, well, s of 0 would be 50. That would be the initial height of the object. Now, v sub 0 represents the initial velocity. Right? So that's the initial velocity, and g is our acceleration due to gravity. Right? So as you look at the position function here, s sub 0 is the initial height of the object, v sub 0 is the initial velocity, and g represents the acceleration due to gravity. Right? Now we'll look at some examples of those in the next video.